Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper data structures. Again, in this module we will be talking about a graph algorithm, and here we are going to talk about topological sorting. We will first see what is topological sorting and then talk about an algorithm that solves the problem of topological sorting of a given graph. Okay. These are the people responsible for the development of this module. The basic learning objectives of this module is to understand what is meant by topological sorting, or the concept of topological sorting. We will also discuss some applications of topological sorting, and we will illustrate topological sorting as we did for the minimum spanning tree using a walkthrough example. Okay. Keywords associated with this module are topological sorting, digraph, reachability, and so on. Now, what is a topological sort? That is the first question we have to explain. Now, topological sort is basically associated with directed graphs. So, if you have a set of tasks and a set of dependencies, that is precedence constraint. What it means is I can do or I have B has to come after A. It can be done or whatever. B has to come after A, C has to come after B. It is not necessarily that way. I mean, not alphabetic order I am saying. So, task A must be done before task B. So, it is basically a task graph you can think of. So, for example, I have to get up before I brush my teeth, I have to brush my teeth before I have coffee, maybe in some cases. I have to take a bath before I dress, again in some cases. I have to come out of the house before I start the car, and so on. And after I start the car, I will reach the office. So, something like this. So, this is precedence of tasks. So, an ordering of tasks that conforms with whatever is given as dependencies. Of course, the graph has to represent these dependencies. Once you have a graph representing these dependencies and precedences, then you have to do a topological sort of the graph, so that you know what are the schedule of activities. So, there is find a topological sort of the graphs, or decide that there is no such ordering, that also can happen. So, before we start off with what is a topological sorting, as I told you, it has all to do with directed graph. So, a digraph is a graph whose edges are all directed. It is a short for directed graph. There are a lot of applications of directed graphs, like one way streets. So, you have all the streets connecting, I mean you have nodal points being connected by streets, and if you have one way streets, then it becomes directed. If it is two way, it is not directed. Then you have flights from one destination to other. Task scheduling. Task scheduling is a typical, any scheduling problem is a typical example, okay, of directed graph. I am not talking about topological sort, I am talking about directed graph. Now, let us look at an application. You want scheduling is a typical application of digraph. So, scheduling, you have an edge A B and means task A must be completed before task B, that is the representation we are using. So, for example, if you take this graph, I have a series of ICS, some code numbers. So, the first task you can do is probably IC1, ICS 21, because it does not have any precedence. So, that can be done. After IC21, I can do IC22, IC23, okay. Then I can do CS 161 and finished with the good life, or I can do IC2 CS 23 if I want to cover all the tasks, then IC CS 23, after which I can do ICS 53. Now, look at 53, 53 can be done only after ICS 21, ICS 22 and ICS 23 is over, okay. While ICS 52 can be done after 23 and only, but 23 can be done only after 21 and 22. So, but 51 can be done only after IC 21, does not have to wait for 22, 23. You understand the problem, that the way when each has to be done is decided by this precedence graph. For example, ICCS 131 is also possible after ICCS 21, and then ICS 51 is you can do after ICCS 151 can be done after 51, but ICCS 53 ends there. Okay. So, these are some you can understand the graphs. Some of things you can see that it is possible to move in two places. For example, ICCS 21, after ICCS 21, I can go to ICCS 22 I can go to ICCS 51 because it does not have any other dependency, or I can go to ICCS 131, but I cannot go to ICCS 53 because ICCS 53 I can go only either after I finish ICCS 2151 or I finish ICCS no, I have to finish 51, 22, 23 and 21, only then I can finish ICCS 53. So, these are issues that we have. Now, reachability, now let us define something else which is called as reachability. A DFS tree rooted at node V, vertices reachable from V via directed paths is called the reachability. So, for example, if you have the graph E given on the left hand side, now you have from E you can reach D, okay, and A, but actually to reach D you have to go from CED and CEA. Okay. Now, if you want to reach F, you have to go from B, and from B you can reach E, you can reach D, you can reach C, and from C you can reach E, and so on. So, you can divide the graph in ways of reachability, because this is important, because how can I reach a node, that is when can I do something, only after some other things are over. Now, let us look at, that is all about directed acyclic graphs, okay, or DAG as it is called. Now, a directed graph and a DAG is different, because a directed acyclic graph called as DAG is a digraph, that is a directed graph which has no directed cycles. So, that if it does not have a cycle, it is called a DAG. Now, a topological ordering of a digraph is the numbering. So, you will just give the vertices, what are the vertices that I can have. Now, and what is this topological ordering, such that for every edge Vi Vj, we have Vi less than j, that means I has to be done, the precedence constraint is I is less than V, so I will be done before j. In a task scheduling digraph, a topological ordering is of a task sequence that satisfies the precedence constraint. So, now we have the condition that a digraph which is a DAG, that is it does not have any cycles, only then you can have a topological ordering. If it has a cycle, it does not have a topological ordering. Okay. So, the one of the orders that you can have for the graph given up in the top is V1 can be the first graph, V2 you can do irrespective of whether you finish V1 or V2. So, V1 V2 is fine, but in order to do V3 or C, that is you can do A and B. So, A is the first V1, V2 can be done. If you do V1 and V2 only, you can do V3, and if you finish V2 and V3 only, you can finish V4, and after V4 only you can finish. The order is A, B, it could have been BA also, does not matter, A, B, C, okay, and then D and then E. So, that is the topological ordering, the V's give the topological ordering. Now, the number of vertices, so what you get as output is a number of vertices. So, that any two vertices U and V in E implies that U is less than V, that we have already discussed. Now, look at the topological ordering of a typical student day. Wake up, study computer science, eat more computer science, or study computer science, take a nap. So, you can eat and then take a nap, it does not matter, or you can take a nap and then eat. So, that those are two either way. Then after you do eating and napping, you study more of computer science. After you finish that, you can write a CS program, but you cannot write a CS program unless you play. So, after more of computer science, you can do a workout and write a computer program, or after more of computer science, you have to do a workout, you have to do play, and then only you can write the computer science program. After you do write the computer science program, only after all that is over, you make some cookies for the professor, then you sleep, and then the next is dream about graphs. So, this is the typical day of a student. You can see that there are some activities you can do in either way, but for example, writing the CS program, you have 3 dependencies there. You have to finish the workout, you have to finish more of computer science, and you have to finish the play. Okay. But then for you to do workout, you should have done more computer science, and you to play, you have to do more computer science. So, 5, then 6 and 7 you can do in any order, but after both only you can write CS. So, that is a very powerful mechanism actually. Now, next is let us for a directed acyclic graph, which I have already said, the graph consists of vertices and edges. So, a topological sort is nothing but a linear ordering of all the G's vertices. Every vertex should be covered V1, V2 to Vn such that the condition is true that every vertex that comes in the linear ordering V1 is less than Vi is less than Vj. So, real world example of getting dressed, which we will see later. Formally, for every edge Vi Vk in E, I has to be less than k. Visually, all the arrows should point to the right in a linear ordering. So, for example, scheduling used for representing the order of tasks. When scheduling task graphs in distributed system is an application, we first need to sort the tasks topologically and then assign them to resources, and most efficient scheduling algorithm is an NP complete problem. Okay. So, for example, here you could have started either at D or C, that is immaterial, but after you do let us assume we start at C, then after C you can do D, after D you can do A, and then G, and then F, and then after A and G you can do B, after B you can do E. So, please note that topological order, as you can see from here, is not unique. It can also be used for compilation to order the modules and libraries that you have to call. Now, this is as we already discussed previously, this is an example of getting dressed. So, here you have after socks you will wear the shoes, but for you to wear shoes you should have first wear the underwear, then the pants, then the belt, but for you to put the belt you should have finished shirt. So, here you have underwear, pants. So, the order will probably be underwear, pants, shirt, belt, tie, jacket, and then socks, shoes and watch. Now, you could have put the watch first also because it is not independent. So, you have here socks, you could have done socks first, underwear, pants, shoes, then you could have had watch, then you have shirt, belt, and then shirt, jacket, tie, jacket. Okay. So, this is the orders. Topological sorts defined for cyclic graphs? No, it is impossible, because if V and W are two vertices on a cycle, there exists paths from V to W and from W to V. So, which do you place in first? So, there is a contradiction. So, any ordering that you do, if you do here for example 1, 3, 2, but for you to do 1 you need to do 2, but for you to do 2 you should finish 1, 3 and so on. So, this will contradict one of the paths, and so topological ordering for cyclic graphs is not possible, it is possible only for DAGs. So, let us define topological sort a little more formally. Is it possible to execute all the tasks in G in an order that respects all the precedence requirements given by the graph edges? That is what we want to do. The answer is yes, but only if and only if the directed graph G has no cycle or it is a directed acyclic graph. Otherwise, we will have a deadlock problem. So, that is what we already said, that it is an acyclic graph. Okay. Now, so topological sort is an algorithm for a directed acyclic graph. Linearly order the vertices so that the linear order respects the ordering relations implied by the arcs. So, for example, here we have 0, 1, 2, 5, 9 is allowed. We have not covered all the vertices, but 0, 4, 5, 9 is allowed. 9 is a dead end, so you can't go further than that. 0, 6, 3, 7 is not possible because there is no edge between 3 and 7. So, 0, 6, 3, 8, 9 is probably possible. 0, 1, 2, 7, 8, 9 is possible. So, there are different ways in which you can do. The last 0, 6, 3, 7 as already discussed is not possible because you have to have an edge. Now, as we already told you, there are many possible topological sorts for a particular DAG. Okay. So, there are topological orders for this particular DAG are 1, 2, 2 you can do 1 and 2 you can do interchangeably also, but anyway 1, 2, after 2 you can do 5 because 5 does not need anything else except 2. Then after 5 you can do 4, you cannot do 7 because after 5 4 needs 2 and 5 which you have done, but 7 needs 4 and 7, so you cannot do. So, 4 is fine. then if you finished 1 and 4 you can do 3. So, 3 is fine, then you can do 6, okay, and you can do 7, but after you finish 4 also you could have done 7 because it is looking only at that. Another is 2 1 5, after you do 5 you can do 4, after you do 4 you can do 7, and then you can do 3 and then 6. Another is 2 5 7, not possible, 2 5 1 2 5 1 4 then 7 3 6. So, there are different topological orders possible. Each order topological order is a feasible schedule, okay, if you take this as tasks. Now, we can model dependency or constraint like these using a graph. So, A stands for waking up, A before B, B stands for taking a shower, and then C stands for eating breakfast. So, A before C, and then B before D, D is leaving for work, and C before D. So, given a set of items and constraint, we can create the graph. Each item corresponds to a vertex in the graph. So, here you have A, B, C, D forming vertex. For each constraint where item A must finish before item B, you have a directed graph. So, you have here A, B, so A before B you have a directed graph, A before C you have a directed graph, B before D you have a directed edge, and C before D you have a directed edge. So, this stands for the constraints. Topological sort would be A, B, C, D. Okay. Now, another example, consider the following clothes to wear. There is not exactly one order to put these items on, but we have to adhere to certain restrictions. Socks must be put on before shoes, we have seen this example before, and so on. So, this is just to give you a feel of that. Now, consider the following CS classes and their prerequisites. So, here you have the class, the subjects classes, and the prerequisites is given. COP 32223 must come before, if you want to take 3330, you should have finished 3223 and 3502. The third can come only after the first two, and then 3330 should come before 3503, 3502 and so on. So, this is an example where you have the prerequisites. So, this can be represented easily with a DAG. Okay. So, the goal of topological sort would be to find an ordering of these classes that you can take. So, this is a very convenient way of deciding what classes to take. So, definition of a topological sort is, it is a method of arranging the vertices in a directed acyclic graph in a sequence such that no vertex appears in the sequence before its predecessor. The goal is, when given a list of items with dependencies, produce an ordering of item that satisfies the given constraints, that is all. In order for the problem to be solvable, as we have already described, there cannot be a cyclic set of constraints. We cannot have item 5 must be completed before 3, item 3 before 7, but 7 has to be for 7 to be completed you should complete 5. So, this creates a deadlock like situation which we cannot do. So, cycle, if you have cycle in that graph, you cannot do topological sort. So, the algorithm is assume in degree is stored. Now, here comes the implementation aspect. So, we assume that with each node we store the in degree. Of course, you know in degree is the number of incoming edges to the node, and repeat under no nodes remain, choose a root and output it, remove the root and all its edges. Then your performance will be of the order of V square E if linear search is used to find a root. Okay. So, but another algorithm is you scan all the nodes and push the roots onto the stack, repeat until stack is empty, you push a root out, output it. For all the nodes n such that Rn is an edge, decrement the n's in degree. If it is 0, then you push it onto the stack. So, that is a possible thing. It is of the order of V plus E. So, still V squared in worst case, but better for sparse graphs. So, this is an example of ordering of a graph. So, you have here D, you can start at D, D and G is independent. So, you could do G, after G you can do A, after A you can do B, if you finish B and D you can do H, you can also do F because after A you can do F. Remember, it is not only one sorting. After H and yeah, then you can do, after J you can do E. So, that is the order here you have. So, starting point must also always have a 0 in degree. If it does not exist, the graph would not be cyclic. A vertex with 0 in degree is a task that can start right away. So, we can output it first in the linear order. If a vertex I is output, then all its outgoing edges are no more useful, since task j does not need to wait for I anymore. So, remove all its outgoing edges. When a vertex is removed, the new graph will still be a cyclic directed graph. So, repeat step 1 and 2, find if there is a vertex within 0 until no vertex is left. So, this is the steps of the algorithm. So, here we have a topological order traversal. You have the number of vertices visitors initially starting at 0 and in use in degrees new. Now, for I is equal to 0 to the number of vertices, try to find a vertex that has in degree 0 and get the edges, and when the edge is there, you remove the edges and see the in degree new in degree, and then you find out. So, algorithm is implemented as a traversal method that visits the vertices in a topological order sort order. We will see in the next module how this can be represented as a depth first search also. So, an array of length b is used to record the in degrees, because that is what you are used, and there is no need to remove vertices or edges. The priority key is used to keep track of the edges with in degree 0 that are not yet visited. So, we will see this algorithm. So, here you have a graph, okay, and there is only one node which has 0 in degree, and that is 0. So, there is only one starting node. It is not necessary, but here we have only one starting node. So, you start the queue with 0. Okay. So, the in degree of 0 is 0, and that is what you start. Now, you have the neighbors of 0, which is 614. So, you are dequeuing the 0 and removing 0's arcs, adjust the in degrees. What do you mean by removing the arcs? Adjust the in degrees of the neighbors. So, you have to change the in degree of node 1, node 4 and 6. So, you minus 1 from the in degree of 1, 4 and 6. So, you are decrementing the neighbors in degrees, that is what you do in the second step, and you output 0 because you have taken it from the queue. Now, the next step is update the values. So, 0 you have finished processing. Now, you update the neighbors, all the 3 when you has only in degree of 1, when you remove, you decrement it by 1, you have all 0. So, you can enqueue all the 3. So, 614 we have enqueued all the starting points, this is the next step. So, now what you have done? You have started with 0, you have decremented the in degrees of its neighbors. When those in degrees are 0, you enqueue it. So, that is the first step. Now, we have to start again. So, you dequeue 6. So, the output becomes 6, and you have to adjust the in degrees. Now, look at what are the neighbors of 6. The neighbors of 6 are 3 and 2 as shown there. When it is 3 and 2, you have to decrement the in degree of 2 and 3. So, it becomes minus 1 minus 1. Now, the next step will show you what the values are. You will see that the values of the neighbors in degree of the neighbors are 1 and 0. So, we have finished handling 0 and 6. So, here you have 0. So, since you have 0, you have to encode that. So, you have 143 as the enqueued output. Okay. So, because it has become 3. Now, comes the next work. You dequeue the next node in the queue, which is 1. So, you adjust the in degrees of its neighbors. So, 1 has neighbors 2. So, you have to reduce its in degree. Previously, it has reduced by 1, now again it is reducing, now it becomes 0. So, that goes into the queue. Okay. So, that goes into the queue. So, you have finished handling 0, 6 and 1, 0, 6 and 1, and 3 you have enqueued. Okay. So, that is what you have done. Now, you are selecting 4. Okay. So, you select 4. So, when you select 4, you have 5 as its neighbor. So, 5's in degree has to be decreased by 1. So, it becomes this, but there are no new start points because none of the nodes have which are not in the queue, that is 5 here in this case has only 1. So, the queue remains as 3 2, and now you dequeue 4. So, you dequeue 4 and take just so its output is 0 6 1 4, you have handled the 5. Now, you take the next dequeue 3, you adjust 3's neighbors. So, 3's neighbors are 8. So, decrease 8 in degree of 8 2 by minus 1. So, it becomes 1, but at that point no more no new start points because of that 3 being taken out, there is no. So, you have 0 4 1 3. So, 0 6 4 1 3. Now, you have to DQ the 2. So, you DQ 2 and adjust 2's neighbors, which is 7 and 5. So, 7 and 5 now the in degrees becomes decremented by minus 1. So, both become 0. Since both become 0, they have to be NQ'd. Okay. So, you NQ 5 and 7. So, and you DQ 2. So, you DQ 2. Now, you DQ 5 and you have 5's neighbor is 9. So, 9's in degree is deleted 1 minus 1. So, you have 9 becoming 1, but no new nodes are no new starts. So, you DQ the next node, which is 5 7 and adjust the neighbors. Now, 7's neighbor is 8, 8 becomes minus 1. So, 8 is input, okay, NQ 8, and now you have to take 8's neighbor, which is 9. So, it becomes 0. So, you have 9 is NQ. Now, 9 has no neighbors. So, then you stop. So, the order is 0 6 1 4 3 2 5 7 8 9. This is a walkthrough example for the very interesting topological ordering problem, where what we have essentially done is we are maintaining a queue to take care of all the nodes which become 0 in degree, because one of its neighbors has been removed from the graph. Okay. That is the basic point, and you have an in degree you have 2 arrays or 2 data structures, one to keep track of who are the neighbors. So, if I remove 5, which is the neighbor that is being affected, 9, then you go to 9 and decrease the in degree. When the in degree becomes 0, you input it into the queue, you NQ it and so on. So, this is what we do. So, is this topologically correct? Yes. 0 6, you could after 0 6, after 0 you could have done 1. So, you do 0 6 1. Now, you can do 4 because that requires only 0. So, you can do 4. Then because you finish 6, you can do 3, and because you finish 6 and 1, you can do 2. Now, because you finish 3, nothing can be done. Because you finish 2, you can do 7, 5 and 7, you can do both, because 4 is also over. So, you do 5 and 7, 5 is first taken. Now, after 5, you can do 7. Now, after 7, 3 and 7 is over, you can do 8. After 5 and 8 is over, you can do 9. So, this is topologically correct. So, what have we done here? We have explained the concept of topological sorting, discuss some applications. Basically, it is a scheduling application, seems very straightforward and easy to understand. So, it is a typical application. We will go into some details of the application maybe later on, but typical is any scheduling task. So, you can see however complicated the precedent constraints are, you can easily do the topological sorting with the appropriate data structures. Okay. And we illustrated the topological sorting using a walkthrough examples, where we showed the 3 data structures that are used. One, a linked list with the nodes and their neighbors. Another is a array with the indexing to the in degree of each node, and then we had a queue where we put the nodes when it becomes 0 in degree because of removal of its neighbors. So, this is what we did in this particular algorithm. Thank you.